Hello friends, and now we will discuss about antenna radiation pattern, that is field pattern as well as power pattern. Okay, so here it is very important topic. What do you mean by radiation pattern? In the radiation pattern, how we can designate it in terms of field pattern as well as power pattern. So if you measure field component from an antenna zone, that is called as antenna field pattern. If you measure the energy dissipated from the antenna in terms of power, that is called as power pattern. So here we are going to discuss about these topics, that is radiation pattern, front to back ratio, antenna beam efficiency and stray factor, radiation power density and radiation intensity. So these are the topics we will discuss along with this radiation pattern. These all are interrelated. And see here, now we are going to take the general structure of the radiation pattern. So we have radiation pattern is nothing but how the energy is radiated from a particular antenna. Okay, that is a field strength or flux density or field produced from the antenna structure. So what will be the shape of the field produced around the antenna systems, that is called as radiation pattern. What will be the shape and how long the field will be distributed, how long the energy will be distributed. Okay, all these things we will discuss under this topic. So pattern here, it looks like in different structures based on the design of antenna systems and the frequency usage and number of antenna in one plane. There are several factors are there for determining the shape of the radiation pattern, right? So here this is the first diagram shows about a dipole antenna is placed at the middle and it distributed electric field. The red color line is the electric field distribution and this blue is the magnetic field distributions. So this plane has been indicated over here and this magnetic field component is indicated over here. So electric field is completely at the shape of 8 and the magnetic field is the shape of circular shape, right? So this is a simple example of radiation pattern. That means what? So this is the field distribution. It looks like the shape of 8. So electric field is produced and it will be mixed, right? So this region filled with electric field component which is produced from the antenna structures. And perpendicularly we have magnetic field that is given in this second diagram, right? So now see the diagram. Here we have clearly explained that how the field is produced. See the first diagram, how the field is fringed out from positive to negative and negative to positive. See here, this is the AC signal is connected over here, and the same structure has been indicated by taking the plane. So see, this plane is nothing but your electric field. The bottom one is showing the magnetic field. So now you can understand from this three-dimensional planes. Yeah. So this diagram shows about the electric field distributions. The bottom diagram shows about the magnetic field distributions. Now, what are the fundamental components are available in antenna radiation pattern measurements? See here. In here, I have kept one antenna in the origin of X, Y, Z planes. Now this antenna radiates maximum field towards the Z plane, right? So this is called as major lobe. So this is the area the antenna concentrates maximum power. Okay, so this is the area the power distribution will be high, and these all the smaller distribution of power, that is power radiated in other regions, right, whose power level is very less when we compare with the major lobe. So this is called as major lobe, whereas the power is transmitted very less in other region are called the minor lobes. Okay, the minor lobes can be classified into two different parts. The one is side lobes. The side lobe appears next adjacent to the major lobe, where back lobe appears exactly opposite to the major lobe, right? So that is the back lobe. Back lobe is exactly opposite to the major lobe. Side lobes are exactly nearby the major lobes, right? So these are the patterns we are going to understand clearly. So our region of interest is the major lobe. Major lobe says about, that is the concentration of maximum power is transmitted in the z directions, right? That is called as major lobe over here. In the other part, the power is wasted. So minor lobe should be minimized. Okay, minor lobe power is wasted over here. The power should be minimized. So as a design engineer, we are going to minimize the power wasted in the side lobes as well as back lobe. So all the entire power should be concentrated over the major lobe in order to increase the maximum efficiency. Clear? Then what do you mean by half power beamwidth and what do you mean by first null beamwidth? We know that beamwidth is nothing but, that is the angular width over which the 50% of maximum power will be transmitted. Okay, this is the angular width over which 50% of maximum power will be transmitted. So here, what is the need of calculating this half power beamwidth? That is nothing but, if we calculate half power beamwidth, then we can locate our receiver properly within this region in order to increase at least 50% of the maximum power. So that is the main significance of this half power beamwidth measurement. The what is the first null beamwidth? This is the angular beamwidth between first nulls of the radiation pattern. Nulls are nothing but, that is the angle there is no power is transmitted. So see here, this is the major lobe, this is the side lobe. Between major lobe to side lobe, there is a direction where there is no power is transmitted. That is called as first null. Similarly, this side, this is the first null. So angular width between the first null is called as first null beamwidth. Clear? So this is the first null beamwidth. So first null beamwidth always almost double the time of the half power beamwidth. That is the relation is given over here. That is the first null beamwidth is equal to 2.25 times of half power beamwidth. Clear? Now, for this side lobe level is very much, it should be reduced less than or equal to 20 dB for satellite and high power applications, and the front to back ratio should be greater than or equal to 20 dB. These are some applications, right? Now the principal patterns are displayed over here. The first diagram shows about the three-dimensional view, the second diagram shows about two-dimensional view, and the last one is showing about the different lobes and the corresponding power distributions, right? So here already we discussed, right? Beamwidth between first null is this, that is the beamwidth between first null. It occurs at the first side lobe to the major lobe. And the third diagram shows about, for major lobe, what is the power level. The next is the back lobes and side lobes and all, what is the power level. So power level versus the angular distribution, it is showing over here. So what do you mean by field pattern and what do you mean by power pattern? Field pattern in the sense to measure field components of an antenna systems, right? So for measuring field component, we are going to take electric field component. So here we are going to take Emax by root 2, that is the 50% of power will be falling within the limit. So if we take Emax by root 2, then the value will be 0.707. So 0.707 is the half power beamwidth we are going to measure in order to get a 50% of maximum power will be transmitted over here. So power pattern is nothing but where power is measured, power distribution is measured, and power is drawn with respect to angles. Field pattern is where electric field is drawn with respect to angles, right? So this is the field pattern, this is the power pattern, and here we are going to take Pmax by 2. Directly we can take, that is the maximum power from this 50%, 0.5 directly we can take. For getting here 50% of power will be calculated based on Emax by root. So what is the relation between power pattern to field pattern? Where power pattern is equal to the square of field pattern. So that is the relation between these two cases. And this is the normalized radiation pattern. How to calculate the normalized radiation pattern from the Poynting vector, right? So Poynting vector power calculation can be calculated by taking the electric field component as well as magnetic field component with respect to theta as well as pi, right? So normalized field, electric field can be calculated by what is the field component we are obtaining with respect to what is the maximum field we have. So we have to take the ratio of field with maximum field component for getting normalized electric field. So power pattern can be calculated by taking the field component whole squared by the impedance of intrinsic or free space impedance. So normalized power pattern can be calculated by taking the what is the power we obtained by what is the maximum power. So by taking the ratio of power obtained to the maximum power, we will get the normalized power pattern. So what do you mean by front to back ratio? So front to back ratio is nothing but it is a ratio between the major lobe to the back lobe, right? For bidirectional pattern, so here it is the antenna radiates both in forward as well as backward. So major lobe and back lobes are equal. So if we take the ratio of major lobe to the the back lobe, then we will get FBR is equal to 1. That is front to back ratio. So in the case of unidirectional pattern, where antenna transmits power only in the one directions, so only towards here, it is the maximum power will be there. So where the back power will be very less. So if we take in this case, the front to back ratio will be greater than 1, because the numerator value dominates the denominator. So we will get FBR greater than 1. So it is occurred in the unidirectional pattern. So bidirectional pattern, for both the directions you will get the same pattern. So it will be equal to 1. So this is the omnidirectional pattern, where power will be radiated equally in all the directions. Now the next one is, what do you mean by antenna beam efficiency and stray factor? What is the need of these measurements? Right, see here, this is your major lobe, and in the radiation pattern we have major lobe over here, and this is the minor lobe, right? This is the minor lobe. So the solid angle or the total area of major lobe is indicated with this. The major lobe is indicated with this. Total area of major lobe is sigma m, and sigma a is the total area, beam area or beam solid angle in the sense. So this is sigma m, this is sigma small m, right? Sigma small m. So total area is the summation of sigma capital M plus sigma small m. So here the beam efficiency is nothing but it is the ratio of how much is the main beam area to the total area. So from this parameter we can understand that what is the maximum signal is transmitted or maximum power is concentrated on the major lobe for the total power, total area. Then stray factor. Stray factor is nothing but ratio of sum of solid angles subtended by the minor lobes to the sum of solid angles subtended by the lobes. That is your what is the area of minor lobe divided by what is the area of the total. Okay. So sigma small m by sigma a. That is what is the power or solid area of this particular minor lobe divided by the total area, that is called a stray factor. So from this measurement we can understand that how much power is wasted. Suppose if this stray factor value is higher, then it says about most of the power is wasted in the minor lobes. From this we can understand, right? So summation of major lobe solid angle plus summation of minor lobe solid angle will be equal to 1. Then radiation power density. So power density can be calculated by taking the half of the power of electric field as well as magnetic field. So here the electric field can be calculated by measuring the patterns, and from this the unit of electric field is volt per meter, whereas the unit of magnetic field is ampere per meter. So we will get watts per meter squared. So this calculation is to measure power density. So next one is, what is radiation intensity? Radiation intensity is nothing but what is the power emitted for every solid angle, right? So see here, so this is the radiated power for every solid angle. So 4 pi is the total amount of solid angle for a sphere, right? So this is called as radiation intensity. So this can be calculated by taking this. So radiation intensity is equal to what is the variation in the power transmission by what is the changes in the solid angles, right? So normally power pattern, you know, that is what is the radiation intensity we got divided by what is the maximum radiation intensity we have measured. So by taking the ratio, we will get the normalized power pattern, and these solid angle calculations and all we have discussed already in the class. So total solid angle of the sphere is, you know that solid angle formula is sigma is equal to integral of d sigma, where integral taken for 0 to 2 pi and integral taken for 0 to pi. So this is your elevation angle, this is your azimuth angle. Azimuth angle changes from 0 to 360 degree, whereas elevation angle changes from 0 to pi degree, that is theta and pi. This calculation already we have discussed in the earlier classes. So total solid angle for the sphere is 4 pi, that is given to these calculations. So radiation intensity is nothing but for every solid angle how much power is radiated, that is called as radiation intensity. I hope this will be useful for your calculations measurements of radiation pattern. So with this we will wind up the today's session. Thank you.